I'm going to talk about vector search. If you haven't heard about vector search yet, it has become an increasingly popular component in generative AI, powering some of the latest large language models, including ChatGPT. In this talk, I'm going to share with you how to achieve high-performance vector search via hardware acceleration. So first, what is vector search? A vector search is essentially a retrieval process. You have some database vectors, then given a query vector, we want to find out the k most similar vectors in the database, or in other words, k nearest neighbors. So what exactly are those vectors in the database, and what are the query vectors representing? That depends on the use case of vector search. For example, if you use vector search in modern search engines, such as Google and Bing, they will use large language model to represent web pages as database vectors. Then, when a user types in a textual query, such as "Who is von Neumann?", the query text is also going to be represented as a vector format. The query vector is then compared against the database vectors in order to determine a list of relevant web pages. If you use vector search in recommender systems, the products or the advertisements are going to be encoded by recommender models, and the user's preference is used as the query vector to find the potential match between the user's interest and what the company offers. And finally, many generative large language models are also enhanced by vector search, known as retrieval augmented generation. You may already heard that these large language models can speak non-factual content. In retrieval augmented generation, we couple a large language model with an external knowledge database, and during generation, the model retrieves relevant knowledge to the current context and use the retrieved content as part of the input for generation. Thus, the generation quality is largely improved. Also, once we decouple the knowledge from the model, it is also easy to edit the knowledge that the model can access. We can just add the latest news to the database, and then the model can access them without retraining. Now, if you run large-scale vector search, such as searching through the web, exact nearest neighbor search turns out to be too hard to afford because it requires linear scan through the full precision database vectors. So in practice, people typically use approximate nearest neighbor search, or ANN search in short, that trades retrieval quality for much higher performance. And the quality metric of approximate nearest neighbor search here is recall, which measures the fraction of true nearest neighbor retrieved by approximate nearest neighbor search. One of the most popular large-scale vector search algorithm is the IVFPQ algorithm. So essentially it combines two components. First, we have the IVF index that prunes the search space. And then we have product quantization that turns high-dimensional database vectors to n bytes of PQ code each. So let's start from the IVF index first. The goal here is to prune the search space as much as possible to avoid the brute force scan. So we have database vectors, and then we essentially run some clustering on top of these database vectors. So we partition the space to multiple subspaces, and each subspace here is known as an IVF list that contains a subset of database vectors. Then, given a query vector, instead of scanning the entire space, I just need to scan a few subspaces that are close to the query vector. In this case, we start from the closest IVF list, and I can also granularly expand the search space, and the search space here is another parameter that we can tune. Of course, the higher the search space, the higher chance we can find the true nearest neighbors, but also the higher cost of the search. Now let's move on to the product quantization part. The motivation here is that given very large vector database, we would like to reduce the memory footprint of the vector search. And we also want to save some bandwidth when scanning those database vectors. In this example, we have n database vectors, each with d dimensionalities. And the first step during the product quantization training is that we partition the database vectors into m subvectors. So here we have m subspaces, each has dimensionalities of d by m. And now, after we have those sub-database vectors, we will run a clustering algorithm within each subspace. For example, in the first subspace, I run a clustering algorithm. I get a list of centroid vectors. The centroid number here is typically set as 256, which we will explain in a second. And then once we have those centroids, what we can do is that for each database subvector, we could approximate by its closest centroid vector. So we turn the first subdata vector first, and we compare it against all the centroid vectors within the same subspace. And then we figure out that 17th centroid is the closest to the database vector, so we just need to store 17 as the number in the database instead of storing the original database subvector. The 17 here is known as the PQ code, and because we only have 256, the IDs here can only be within that range, and we can only use 1 byte of PQ code to store a database subvector. And then given a database vectors divided into m subvector spaces, we only need m bytes of PQ code to represent a full database vector. Now, during the search, we will also partition the query vector into m subspaces. So we start from here, and essentially we compare the query vector against all the subcentroids first to construct the distance lookup table. So compare the first subvector of the query of all the centroids, and I compute all these 256 centroids in the distance lookup table. Once we do that, when scanning the database vector, we can use that distance lookup table very efficiently. For example, if I compare the first subquery vector with the first PQ code in the database vector, I just need to use the 17 as the address to fetch a distance from that lookup table, because I already computed all of those distances beforehand. We repeat this process for other dimensionalities, and essentially we will have m looked up distance for each product quantization vectors. We essentially add up those 16 distances, and now we can have the distance between the query vector and the quantized database vectors. And because we scan many of those database vectors during the search, the distance lookup table will be reused many times, and the computational efficiency is appropriately improved here. Putting the IVF index and product quantization together, we have the very popular IVF PQ algorithm, and here is a high-level overview of the workflow. So when we receive a query vector, it starts by doing a simple transformation of the query vector. And then we have the index scan part, where we compare the query vector to all the centroids of those IVF lists. Then we select a subset of lists to scan, which are close to the query vector. After that, we construct distance lookup table per list in order for fast distance estimation. We then compute the distance between query vectors and the database vectors. Eventually, k nearest neighbors are collected and returned to the user. So in this project, given the rising importance of vector search and the popularity of IVIPQ algorithm, we ask, can we build a specialized hardware accelerator for IVIPQ? Well, it turns out it is not that easy, as there are several challenges when building such an accelerator. First, we have 6 different search stages, each have different workloads on it. So in order to build a hardware accelerator, we have this interstage heterogeneity where we need to build different processing element for different search stage. And then, even within a search stage, there can be multiple types of hardware within the search stage that has different performance and resource consumption trade-offs. And thirdly, given cheap resources, how do we allocate the limited resources to all 6 stages Do we allocate more resources to stage 5 or do we allocate more to stage 1? And also, how many processing elements and what is the type of processing elements to peak per stage is also another question. So you may ask, why not just run some profiling first? So we identify the bottleneck stage first, so we can optimize the bottleneck stage as much as possible. Well, it turns out that there are many parameters in IVIPQ algorithm, and all these parameters can change the bottlenecks dramatically. For example, we have the number of clusters in the index. We can determine what is the number of clusters to search per query, and also what is the k nearest neighbor to return. For example, here we show you the profiling information on GPU where we tune k, which is the number of results to return per query. We evaluate k from 1 to 1000 and break down the time consumption per stage. As you can see here, the time consumption of the k selection stage increases from 26% all the way to 78%. So drastically different performance bottleneck when we are just tuning the k. And similarly, if we tune other parameters, the bottleneck is also going to shift accordingly. So in order to figure out how to build an efficient accelerator for IVIPQ, we take a step back and think about what is really needed in the deployment scenario. To this end, we talked to some industry partners and we figure out this is a typical scenario. So we have some users. User will offer their dataset and they say, if I give you some sample query, here is the recall requirement that I want to achieve on this dataset. For example, over this 1 million query, I want a statistically average recall of 90%. So given this scenario, we ask what is the method that we can use that taking this user's requirement and automatically determine what is the optimal hardware design for it. And then, accordingly, what is the optimal algorithm parameter that we should use to run on top of that hardware. And finally, can we automatically generate ready-to-use accelerator so we hide all this hardware complexity from the users? To answer these questions, we propose FANS, which is a hardware algorithm co-design framework for vector search. We use FPGA to prototype FANS because of the huge design space within the IVIPQ algorithm. So the key idea of FANS are several folds. First, we want to consider the algorithm parameters. Essentially, we want to measure the relationship between them and the recall requirement on the specific dataset. And then we want to consider hardware designs where we have multiple valid designs, both within a single stage and across multiple stages. Also, how do we allocate the on-chip resources across the 6 stages? We have the algorithm side information and hardware side information now. We can model the performance of each combination of the parameter and hardware design. After that, we choose the most performance combination of them and we generate the respective optimal hardware accelerator on FPGA. Here shows you a high-level overview of the FANS workflow, which is quite complex, but I'm going to show you how we do it step by step. So first on the algorithm side, given the user-provided dataset, we want to try out different IVIPQ parameters. Essentially, we want to explore the relationship between parameters and recall. In this table, you can see the first row represents one of those experiments where we use one set of index setting. In this set, we use 1024 as the number of IVF lists, and for each vector, we compress it to 16 bytes of PQ codes. And in order to achieve a recall of 80% for the 10 nearest neighbor, we evaluate on average what is the minimum number of lists to scan per query in order to achieve that recall. So here, we figure out that at least we need to scan 12 out of the 1024 lists in order to achieve this recall. This information is very useful for performance modeling because with this, we can essentially model what is the expected database vectors to scan per query and what is the index list numbers. Essentially, we can model what is the workload per 6 stage stages on average. And then on the hardware side, we start from building the basic hardware processing elements, the PEs. And if there are multiple valid designs per stage, we build multiple types of PEs. With those basic PEs, we can then model the resource consumption as well as the performance per PE. The resource consumption is more straightforward because we just generate the hardware, run the synthesis, and we observe what is the FPGA resource consumption of each PE. For performance modeling, because we already know the architecture of each PE, we know the pipeline depth of it, and we know what is the pipeline initiation interval, and then given a frequency expectation, we can now model what is the time consumption of a PE takes to process, let's say, n input elements. With those basic hardware PEs, we can now combine them of all 6 stages into an entire accelerator. So we can combine arbitrary number of PEs per search stage into an accelerator, and the accelerator is valid as long as the total resource consumption is within the FPGA's resource budget. So in our case, the FPGA contains VRAM, lookup tables, flip-flops, and DSPs, and we want to make sure that none of those resources are overconsumed given this accelerator design. So now we have the both worlds. We have the information on the algorithm side where we capture the relationship between parameters and recall, and we also can estimate the workload per search stage. On the hardware side, we will have a list of valid accelerated design, each specifying what is the number of PEs per stage and what is the architecture of each PE. And putting them together, we can now model the performance of the overall search performance of the entire accelerator running a specific algorithm setting. With that, we can derive what is the optimal combination of the both worlds, and we can start to do the end-to-end generation of the optimal hardware accelerator. So essentially here we use the code template that we got from those basic hardware PEs, and then we stick them together to generate the respective hardware we want. Here shows you an example design where we have all 6 stages marked in different colors. As you can see in this figure, we use a data flow accelerator. So essentially the data parsed by hardware FIFO to the other stages, and at any moment of the search, there are up to 6 queries in this 6-stage pipelines. And for each stage, there can be multiple PEs to run the workload in parallel, and there can even be heterogeneous PEs as long as the performance of the stage is maximized. Here we use a table to show that fans generates different hardware for different users' requirement. In this table, on the top, we have the FPGA baseline. Essentially, this is the designed FPGA accelerator without considering those co-design framework. Essentially, for the 6 stages, we want to balance the hardware resource utilization across all those stages and try to fit everything on the FPGA. And then on the bottom, we have the fans generated design where we use this co-design flow. To zoom in, for those 3 different recall requirements with different case, the 3 generated hardware design runs different algorithm parameters. Essentially, we use 3 different types of indexes because they are suitable for different users' requirements. And also, within the search stage that we use the same type of PEs across the accelerators, we found out that the number of PEs are different in order to maximize the performance for the specific algorithm parameter settings. And for the stages with different architecture options, such as the case selection stage, we offer 2 different options, and the accelerator picks different options to maximize the performance for different algorithm parameters. And eventually, we have the predicted queries per second as the throughput metrics for different accelerator. To compare fans with CPU and GPU baselines, we use CPUs, GPUs, and FPGAs that are manufactured within the similar generation of technology, we not only compare to CPU and GPU baselines, but also the FPGA baselines that we mentioned before, where we try to balance the resource consumption across the 6 stages on FPGA. For software, we use FICE, which is the most popular library for protocol-based approximate nearest neighbor search. FANS is developed by Meta, and it is known for its very high performance for not only CPUs but also GPUs. For FANS, we developed the FPGAs by Vetis HLS. We evaluate the performance on 2 most popular vector search benchmark, the CIF and the deep datasets that contains vectors of different dimensionalities. So here we show you the throughput speedup over the CPU and FPGA baselines. On the x-axis, we not only evaluate various algorithm parameters for the FANS design, but also the respective parameters for the baselines for CPU and FPGAs. As you can see in this figure, we achieve up to 20x and 30x speedup over the FPGA and CPU baselines respectively. It is worth notice that even for the software and FPGA baselines, it is important to tune the parameters to maximize their performance. But even compared to the most performant baseline, FANS do show a clear advantage over them. And also, the FANS-generated accelerator achieves much more than 90% of the predicted performance, showing the effectiveness of the performance model we have. Now, what about the throughput comparison to the GPU baseline? Well, it's hard to do a completely fair comparison between FPGAs and GPUs because the current generation of GPUs are much more powerful than FPGAs. They offer 2 orders of magnitude higher flops and 1 order of magnitude higher bandwidth. So it's not surprising that GPU still outperforms FANS in terms of throughput, even if FANS use this co-design workflow. However, in terms of latency, it is another story because GPUs have shown high variance in its latency. There are some long tail runs, which is really harmful for scale-out experiments because in the scale-out experiments, the performance is essentially determined by the slowest GPUs. And as you can see in this plot, where we show scale-out accelerator experiments up to 8 accelerators, the GPUs are already slower to FPGAs by 7.6x in terms of 95% tile latency. So far we have done a grand design space exploration by using FPGAs, but given the rising importance of vector search, what about future ASIC designs? Because obviously, ASICs cannot be so easily reprogrammed for different users' requirements, and the shifting bottlenecks is a big problem for ASICs. Well, we found out that there must be some algorithm-level adjustments to mitigate the problem. First, scanning many quantized database vectors are essential to achieve high recall because we want to have a reasonably large search space in order to have a higher chance to find the nearest neighbors. However, we found out that for the index scanning part, there's something that we can trade off. Right now, we're comparing the query vector to all the IVF list entries. So this is a brute force scan, and if we have many of those IVF lists, the index scan part can be a performance bottleneck. However, we can also treat this step as another approximate nearest neighbor search if this becomes a bottleneck. We can construct another index on top of this centroid vectors. So once we do this, the performance bottleneck is pushed to the PQ code scan and the case selection stages. And if this is the stage, we expect future architecture to combine a CPU for fast index traversal based on ANN search and an ASIC for scanned quantized database vectors and collecting the top K results. So to conclude, vector search is the core of many applications, including large language models. The IVF-PQ algorithm have multiple search stages and shifting bottlenecks. To this end, we propose FANS, which is a hardware algorithm co-design framework for IVF-PQ-based vector search. Given a user requirement on a specific dataset, we use a performance model to guide the accelerator design, and we automatically generate the optimal hardware design running the optimal algorithm parameter, and all this complex process are hidden from the users. Eventually, we achieve up to 20x and 30x speed up over the CPU and FPGA baselines, respectively. So I'm happy to conclude here, and I'm looking forward to answer all of your questions you may have.